Hey gang, I wanted to post another video kind of reviewing a few of the more difficult probability problems that we looked at. So here's one where we want to find the probability of drawing 4 of a kind. So that means it could be 4 kings, 4 tens, 4 eights. And what a lot of people did wrong when they answered this question on the quiz was they found the probability of picking 4 of a specific number, okay? But this just says 4 of a kind, so it could be any 4. So what we need to think about here is the first card. Well, first card doesn't matter. We have 52 choices out of 52. Once we draw that first card though, now maybe it's 4s. Well, how many 4s do we have left? We only have 3 4s left. And we have 51 cards left. And so now we've drawn the second 4. Now we need to draw the third 4. Well, we only have 2 left, and we have 50 cards left. Now we need to draw the last 4. We only have 1 4 left, and we have 49 cards left. So this first fraction is just 1, so 1 times all this other stuff, so we don't even really need this first fraction. And then we could take 3 times 2 times 1, that would be 6, over 51 times 50 times 49 is 124,950. Okay, and then we could simplify that or turn that into a decimal. But if we're looking for 4 of a kind, this is how we would do it. Now, if I said, what's the probability of getting 4 4s, that's different than 4 of a kind, because now I've given you a specific number. Okay, so our first fraction would have been 4 out of 52 because there are only 4 4s in the deck. But because we were looking for just general 4 of a kind, that first card could have been anything. Okay, all right, let's look at another example. Here you're playing a game with your friend. You're each going to roll an 8-sided die. Player 1 will win if the highest roll is a 6 or less, and player 2 will win if the highest roll is a 7 or an 8. So all we really need to think about here is what's the highest roll. Okay, so basically anytime there's an 8, that's going to be the highest roll, and so we know player 2 is going to win for those. So I'm just going to put a 2 in this entire row and in this entire column, because those would all be, the highest number would be 8 on one of the dice. So player 2 would win. Player 2 would also win if the highest roll is a 7. So player 2 would also win in that entire row and this entire column. Okay. Now, player 1 wins if the highest roll is a 6 or less. Well, notice now the box that I have left here, the bottom right corner, they're both 6s. That's the highest it could be. So player 1 would win there, and that means player 1 would win in all of these other cases. Okay? And everything in between. So what does that mean? Well, if there are 8 possibilities on each die, 8 times 8 is 64. So there are 64 possible outcomes here. Of those 64, 6 times 6, 36 of them, player 1 wins. And then the other 8, 16, plus 6 is 22, plus 6 is 28. 28 out of 64, player 2 wins. Okay? So in this case, it would be better off being player 1, because you win 36 out of the 64 times. Player 2 wins 28 out of the 64 times. Okay? So this is a way that you can set up a problem like this. All right, and lastly, I want to look at our conditional probability example. Again, I'm just going to show you another way of solving this. So the last time we looked at an area model. This time I'm going to use a tree diagram. So I'm just going to draw my tree down here at the bottom. And we have somebody that uses, and we have people that do not use. So I'll say N for non-users. Now it says that 15% of applicants use drugs. So we're going to put a 0.15 up there. and that means 85% or 0.85 do not use drugs. Okay? Then we're giving people a drug test, and that drug test could come back positive or it could come back negative. And that's whether or not they're using drugs. Doesn't matter. Could be positive, could be negative. Now it says that the test is not perfect. It returns a false positive 8% of the time. So that means people who aren't using, so down here, are going to test positive 8% of the time, or 0.08, which means that they'll test negative 92% of the time, or 0.92. And a false negative, and a false negative 12% of the time. So a false negative would mean that you're using drugs, but it comes back negative. So 12% of the time there, 0.12, which means it's going to return a positive result the other 88% of the time, or 0.88. Okay, so we could set up a tree diagram like this to help us answer this question. So now let's look at what the first part is asking us. Calculate the probability that a randomly chosen applicant doesn't use drugs, given that they test positive. So we start here, given that they test positive. So we're really only concerned with the positive test results, these two branches. So we need to calculate those probabilities. And remember, along a branch, you multiply. So we're going to take 0.15 times 0.88, and that gives us 0.132. And then we're going to take 0.85 and multiply it by 0.08, and that gives us 0.068. So these are the two positive test results. Now we want the probability that a randomly chosen applicant doesn't use drugs. So the ones that don't use drugs are down here. Okay, so 0.068 are the ones that don't use drugs. The total number of positive test results is 0.068 plus 0.132. Okay, so that's 0.068 divided by 0.2, which comes out to be 0.34, or 34%. Okay, and let's just go back a few slides, and we can see that that's what we got for our answer when we did this using the area model. All right, now just to show how we can use this with the second half of this example, calculate the probability that a randomly chosen applicant uses drugs given that they test negative. So start here, given that they test negative. So now we do want to know these other pieces here. So we would take 0.15 times 0.12, and that would be 0.018. And then we would take 0.85 times 0.92, and that would be 0.782. Okay, so now find the probability that a randomly chosen applicant uses drugs. So that would be these people up here. So 0.018. We have to divide that by the total of negative tests. So 0.018 plus 0.782. So that's 0.018 divided by 0.8, which comes out to be 0.0225. Okay, or 2.25%. And let's just go back, take a look at what we got the last time. Sure enough, 0.0225 or 2.25%. So you can use an area model, or you can use a tree diagram to help you with these conditional probabilities. So hopefully that helps answering some of these more difficult probability questions.